So if we have a triangle, and I know that this is 5 and 12, and I want to find like side C or angle theta. Talk me through it. Go ahead, Monty.
If you want to find C, you use the Pythagorean theorem.
You got it. 5 squared plus 12 squared equals C squared. 25 and 144, 169 equals C squared, so C equals 13. Okay. Monty Collins, want to tell me theta? Okay, so we can set up a trig equation. The tangent of theta is opposite over adjacent, and then we could use our calculator and do inverse tangent to solve for theta, making sure that you're in radians if you want the angle in radians, or degrees if you want it in degrees. Fair enough? Say yes. You should have all been jumping at that. We love that. I could have asked that in geometry, right? Is that a geometry question? Is that when you learned right triangle trig? Okay. Well, if we take that question now, and that is the worst triangle I've ever seen. Maybe not the worst. And I ask about, oh, I shouldn't do that. Maybe I don't know what that is. And let's say that this is 100 degrees. What can you start telling me about C and theta now? Got any tricks up your sleeve, Elizabeth?
Well, I'm not sure, but it could be an isosceles triangle, so the other triangles could be.
They could, but actually tell me why you know it's not.
Because C's the longest leg and the other two aren't equal to each other.
There you go. Good. All right. I like that.
If you squint, maybe C is the longest.
No. Thank you, though. What can't we do? Definitely not. Why not? Okay, so Pythagorean theorem's out. What else can't... Yeah, we can't do our trig ratios because they're also based on right triangles. Right? Alright, so, can I give you a little help? Say yes. Okay, so here's what I'm going to do. I'm actually going to, I think, call this... I'm going to do the same triangle, but I'm going to do it with letters. And all I really need you to do is follow along and agree with me. Okay? And let's see, let me get the right letters so it matches up to the one that's in your book. And then when we're done, I will give you, when we're done, I'll give you like the equation. Like I'm going to derive a helpful equation for you that will help us. So in a general triangle, A, B, C, we call the vertices capital letters A, B, and C, and they stand for the angles. So if I say angle A, I'm talking about capital letter A. Is that okay? And then in a general triangle, we label the sides across from the angles with lowercase letters. So side A is lowercase a, and that's directly across from angle A. Side B is lowercase b, and that's across from angle B. Do you see how they correlate? So when we're talking about a general triangle, that's the general idea. That's our assumption that we make when we say triangle ABC and we label it with sides and angles. Okay? Unless we state otherwise. So the problem with this triangle, Danny, is it's not a right triangle. So here's what I'm going to do. I'm going to help matters along, and it's going to allow me to set up a few equations that will allow me to derive a special relationship. Okay? So again, you don't need to frantically write. All you need to do is follow along and agree with me. And if you don't agree with me, you got to say, hey, that doesn't make any sense. So the first thing I'm going to do is sneaky. I'm going to make not one right triangle, but I'm going to make two right triangles. Is that all right? All right. And this is actually going to be the key to it. I didn't have a right triangle, but now maybe I have two right triangles, and that's going to be very helpful. So I'm going to call this X. And what does that make this? Michelle, loud and proud. A minus X. I don't know that they're equal, right? But if this whole thing is A, and that piece is X, what's left over? A minus X, right? Algebra 1, like it's the piece that's left over. Is that all right? All right, and this dotted line doesn't have a name, so I'm going to call it H. Height. Is that all right? Okay, so first, let's look at this triangle. What kind of triangle is it? All right. Hey, how you doing? So someone give me a helpful relationship between the sides of this right triangle. I love it. It's the Pythagorean theorem, okay? So let's see. A squared minus 2ax plus x squared plus h squared equals c squared. You okay with how I foiled that? I did it fast. Is it all right? Algebra 1 or Algebra 2? 2? Foiling?
A little bit of one.
All right. All right, so I have that first relationship. That's going to be helpful. Well, I'm going to go over here. Miles. I have a green triangle. Give me the Pythagorean theorem over here.
X squared plus h squared.
That's awesome. Can I tell you why that's absolutely awesome? Because guess what? I have an x squared plus h squared here, and I have an x squared plus h squared there. You ready for the big switcheroo? All right, a squared minus 2ax, but instead of x squared plus h squared, I'm going to say plus b squared equals c squared. Now, this is starting to look a little like something. Not exactly, but a little like something. What does it sort of look like? Pythagorean theorem, doesn't it? Almost, right? I could write a squared plus b squared, but then I have this minus 2ax, which is sort of crazy, equals c squared. So I almost have the Pythagorean theorem. It's not going to be exactly the Pythagorean theorem. The last thing I'm going to do is come up with a relationship for x. And over here for x, are you okay if I say that, hey, the cosine of angle C, that's this angle, is x over b, adjacent over hypotenuse? Does that work? In the green triangle? So, in other words, x is equal to b times cosine C. And now I'm done. I have a squared plus b squared minus 2a, but instead of x, I'm going to write b cosine C is equal to c squared. And this is a relationship known as the law of cosines. And here's the beauty of this relationship. This relationship works for any triangle. Not just right triangles, but any triangle. It's based on the fact that any triangle can be broken into two right triangles, but the triangle itself, the big triangle, doesn't have to be a right triangle. So the beauty is it works for any triangle. The sort of bummer is it's not as easy to remember as the Pythagorean theorem, right? A squared plus b squared minus 2ab cosine C equals c squared. So we should do an example of this.
Is that second C the side?
Oh, I'm so glad you asked. okay? We should do an example of this, and Danny points out before we even do an example that there are two different C's in here, okay? One is a small c, which stands for the side, so that's a side. And one is a capital C, it's a big C, and that stands for the angle. Okay? And not only that, but it's really important where the relationship of where A, B, and C all are. So we should take a look at how we could apply this relationship. But this works for any triangle. It doesn't have to be a right triangle. But the trade-off is it's a little harder to remember than the Pythagorean theorem. Hey, just out of curiosity, if angle C was 90 degrees, yeah. If angle C is 90 degrees, the cosine of 90 is 0. And you get the Pythagorean theorem. Okay? It's tricky. I like it. It would have been shocking if it didn't happen that way, right? Like, it would have sort of stunk. I agree. All right, so let's see. I'm going to make some room by deleting some of this, and then we will keep our law of sines there, and we'll do like an example. Okay? So you agreed with me? Was there anything that was too sneaky that you didn't get? No? All right. So let's see. I think before we had something like, 12 and 14 and 100 degrees that we had? Okay, so when you label your triangle, it doesn't matter what you decide to call A, B, or C. The important thing is that the angles opposite the sides correspond. So, for example, I'm going to call this side C because it's what I'm looking for. Okay? I'm going to call this side A and this side B, and that makes this angle C, this angle A, and this angle B. They didn't label that triangle for me, but do you see how I sort of contrived those labels? Mm-hmm. So this is what the law of cosines would say. It says a squared plus b squared minus 2ab cosine c is equal to c squared. A squared is, all right, b squared is, yeah, that's what I thought you were going to say. Minus 2 times 12 times 14 times the cosine of, yeah, what's C? 100. As a matter of fact, can we equal C squared? Can you see that angle C is always going to be between side A and side B? Is that true? Like if we draw another triangle like this and I have A, B, and C, that means angle C is over here. Can you see that angle C is always going to be between side A and B? Mm-mm. Angle C, not side C. Go ahead, draw me a triangle where angle C is across from side A and B.
No, across from side C.
Oh, it's all, yeah, yes, it's defined to be across from side C. It's always going to be across from side C, but what I want to try to show you is, if you know two sides and the included angle, right, do you remember that word included angle? Included means the angle that's formed by those two sides. That's a perfect candidate for the law of cosines. The law of cosines is perfect help if you know two sides and the angle between them. It's also not too bad if you know three sides and you're looking for the angle, right? Like, the law of cosines will also find you the angle if you know three sides. All right. I'm going to need a little help on your calculators. So 12 squared is 144, plus 14 squared is 196. Now you're going to have to do minus the quantity, 2 times 12 times 14 times cosine of 100, making sure that you are in degrees. So you're going to have to subtract that whole quantity, which is going to be 28 something cosine. Two times 12 times 14 times the cosine of 100. You get negative 58 about. So you get 144 plus 196 minus negative 58 point something equals c squared. So you need to add 144 plus 196 plus, right, 144 and 196. So 144 plus 196, and now you could actually subtract second answer, which is going to be minus a minus, and you get around 398. Okay. And then what do you have to do with that? Take the square root of your answer. And you're at 19.95. Hey, C is equal to around 19.95. And you couldn't get that any other way. That's pretty cool, huh? Say yes.
Yes.
All right. Alternately, if you knew you had three sides of a triangle, like 7, 8, and 10, and then you wanted to find any angle, let's say we want to find this angle here, we could use a squared plus b squared minus 2ab cosine c is equal to c squared. Now, in order to use that successfully, you have to be thoughtful about what you want to call sides A, B, and C. How should we set that up if we want to find that angle between 7 and 10? Thought or idea? Peter?
A or B could be 10 or 7.
Yeah, I agree. Peter says, look, if we're looking for the angle, then A and B should be the sides that form that angle. That's perfect. So that makes 8 side C, and it makes this angle C. So I could set up 7 squared plus 10 squared minus 2 times 7 times 10 times the cosine of, I don't know, is equal to 8 squared. And you could solve that. Okay? I'm not going to do it right now, but that's something you could solve. Okay? So the law of cosines will find you an angle if you have 3 sides, or it will find you a side if you have 2 sides and the angle between them. Can I show you where it won't help you at all? Say yes. If you have 7, 8, and 30 degrees, actually 30 degrees is a bad number to pick. No, that's fine. It's a fine number to pick. The law of cosines won't help you, because no matter how you set it up, you're not going to have the sides and angles that you want.
Can't you figure out the other side then?
If you want to find out this side, we need the law of cosines. We can't use the Pythagorean theorem. And if we want to find that side, then we need a squared plus b squared minus 2ab cosine of angle C. That's this angle. I don't know that angle. It's a bummer. Like, you're sort of thinking the law of cosines is great, it'll solve anything, but it won't. You sad? Don't be. I got something else up my sleeve for you. Back to this triangle. Let's see. Actually, let's not do that. Let's just get rid of this. All right, so the same triangle that we started with, you don't have to frantically write this down. Just agree with me, okay? Sine of angle C is opposite over hypotenuse. Okay. Is that all right? Sine of angle B is opposite over hypotenuse. Is that okay? Okay. H is equal to B sine C. H is equal to C sine B. So in other words, B sine C equals C sine B. You want to know a really easy way to remember that? Sine C over C is equal to sine B over B. And whoopsie daisy. And actually, if I redrew the triangle differently, I could also say the sine A over A is equal to all that. That is called the law of sines. The law of sines says that the sine of any angle over its side is in the same ratio as to the sine of any other angle to its opposite side. And that's actually really helpful. The law of sines says that the sine of any angle in a triangle, the ratio of the sine of the angle to its opposite side, is proportional, is in the same ratio as the sine of any other angle in that triangle to its opposite side. Okay? So they're all in the same ratio. And when you think about it, it makes sense. If C is a small angle, what's going to be true about side C? It's going to be a small side, right? It's the alligator thing, right? The bigger the alligator opens, the bigger the opposite side. Did you do this in geometry?
No, we didn't get the alligator.
Like the longest side is opposite the biggest angle in a triangle? Yeah, okay? That's the alligator, right? If the alligator opens its mouth really wide, that's a big angle. There's a side opposite that is really long. If the alligator closes his mouth, that's a very small angle, and that side opposite between its teeth is very, very small, okay? So that's what the law of sines says, and if we go down back to here, this is the perfect candidate for the law of sines. Because we could say, hey, the sine of 30 degrees over 8 is equal to the sine of theta over 7, right? Sine of 30 over 8 is sine of theta over 7, right? And you can solve to find out what theta is, and then you could find all three angles, and then you could use the law of sines or law of cosines again. Is that all right? All right, so look. You are going to get practice solving triangles tonight. And when we say solving triangles, they'll probably give you a couple angles and a couple sides, but as opposed to when you were asked to do these problems before, the triangles were right triangles. The triangles aren't going to be right triangles this time around, but you have the law of sines and the law of cosines to help you out. There's one instance that we haven't talked about where the law of sines leads you into a bad situation. All right? I don't think there are any from your homework tonight where it leads you into a bad situation. But tomorrow we'll talk about when the law of sines, even the law of sines can be disheartening. All right? But you have two new tools that you never had before, and you have them because of trigonometry. And it's because you're that good with trig now that you can use your two brand new rules. All right? We good? All right. So give the homework a shot tonight. Draw pictures. Label your sides. Ask yourself, should I use the law of sines or the law of cosines? And then we'll talk about it tomorrow, and then we'll figure out where the law of sines will lead you into, lead you down the wrong path. And when